Get this, we're diving into a paper today that's asking, what if black holes, don't disappear the way everyone thought? Expert speaker, you up for this? This one's wild.
Absolutely, yeah. It's a real head-scratcher. This paper is suggesting they could actually be the dark matter everyone's been hunting for, and get this, we might even be able to hear them.
Okay, well, hold on. Back up here, black holes. I need you to break this down for me.
I hear you. We're talking about gravitational waves, those ripples in space-time. This paper, Inflationary and Gravitational Wave Signatures of Small Primordial Black Holes as Dark Matter. It's got Barker, Gladwin, and Zell diving deep into how these tiny ancient black holes could be making waves, literally, that we might just be able to detect.
Okay, so mini black holes, gravitational waves. But to even get there, we got to tackle this whole evaporating black hole thing. Didn't Stephen Hawking pretty much nail that coffin shut?
Well, that's been the working theory, right? Hawking radiation, the idea is that black holes slowly leak energy and shrink over time. Smaller they are, faster they vanish. So, teeny black holes from the early universe. Long gone. Toast. At least that's what we thought.
But this paper says, hold my cosmic coffee.
Pretty much. They're saying the closer a black hole gets to this size limit, the Planck length, the weirder things get. Like, our usual physics just starts to break down.
Okay, the smallest anything can possibly be, we're in the quantum realm now.
Head first. And that's where they introduce this idea of, get this, memory burden.
Memory burden. Sounds heavy.
Think of it like this. A black hole's entropy, it's basically how much information it's crammed inside. Like, imagine trying to stuff an entire library into a shoebox.
Yeah, good luck with that.
Exactly. At some point, something's got to give. This paper's saying that information overload, that memory burden, could actually slam the brakes on black hole evaporation.
So instead of poof, gone, they stick around. Maybe even become dark matter.
Now you're getting it. Astronomers have been looking for something, anything, that fits how dark matter behaves. And these potentially long-lived mini black holes, they just might be it.
And this paper actually lays out how that would work.
Oh yeah, they go there. They're saying if this evaporation thing is wrong, it throws open a whole new range of sizes these primordial black holes could be, like the ones born right at the beginning, Big Bang babies.
Primordial. Okay, I like it.
And here's the kicker. These black holes, they wouldn't mess with stuff like Big Bang nucleosynthesis, you know, that crucial early phase where all the light elements got made. Other dark matter candidates, they screw with that whole process if they're the right size, but these mini black holes, they slide right under the radar.
So they work with what we know about the early universe. But hold up, if these things are so tiny and have been hanging out since, well, forever, how do we even find them? It's not like we could just, shine a flashlight into the early universe.
That's where those gravitational waves come in, and it gets even more mind-blowing.
So these gravitational waves, they're like what, the black hole's calling cards?
You could say that, imagine a giant cosmic bell ringing out from the very beginning of the universe.
And we might actually be able to hear it. Okay, now I need the crash course version. What are gravitational waves to get? Beyond ripples in space-time.
Right.
My brain needs a picture.
Okay, so picture this. You throw a rock into a pond, right? What happens?
Ripples, it makes ripples.
Exactly. Gravitational waves are kind of like those ripples, but instead of water, they're stretching and squeezing space-time itself.
But these ripples, they're made by something massive happening.
Yeah, we're talking huge cosmic events here. Stuff like black holes smashing into each other, stars exploding, that kind of stuff. And the cool thing is, these waves, they travel across the universe basically forever, like echoes of these events billions of years ago.
Okay, so back to our tiny black holes. This paper is saying they made their own set of ripples way back when.
They're saying those crazy fluctuations in the early universe that could have made black holes, well, they would have squeezed and stretched space-time like crazy, sending out these gravitational waves.
And each set of waves is unique, right? Like a fingerprint for whatever made it.
You got it. And this paper goes even further. They're not just saying, hey, maybe there are waves. They actually calculated what these waves might look like.
Okay, drum roll. What'd they find?
Hold on to your hat, they're saying. These waves, they'd be at super high frequencies, way higher than anything LIGO or Virgo can pick up.
Wait, those are the big deal gravitational wave detectors, right? The ones that, won the Nobel Prize?
Yep, those are the ones. Amazing instruments, but they're tuned to hear lower frequencies. Things like those black hole collisions, these primordial waves from the tiny black holes.
So it's like what? We're trying to listen to a dog whistle, but we've only got a radio.
A very, very sensitive radio. But you're getting the idea. We need a whole new kind of instrument to even try to hear these whispers from the early universe.
So what scientists are building, A cosmic ear trumpet or something. What's the plan?
It's actually pretty cool. One idea is to use something called resonant cavities. Think of it like this. Remember those tuning forks back in science class?
Yeah, you hit it.
It vibrates at a specific frequency, right? Well, imagine that, but instead of sound waves, it's designed to resonate with these high-frequency gravitational waves.
Okay, so the wave passes by, sets this cosmic tuning fork humming.
You got it. And if we can build these detectors sensitive enough, we could pick up those tiny, tiny vibrations. That's the hope, at least.
That's wild. But even if we can build it, this whole thing hinges on these mini black holes actually being out there, right? If that memory burden thing is a bust, then.
It's all back to the drawing board. This is why this research is so exciting. It's pushing the limits of what we know about black holes, dark matter, the whole shebang.
So let me get this straight. We're talking about rewriting what we know about black holes, listening in on the universe's oldest secrets, and maybe, just maybe, figuring out this whole dark matter thing. And it's all thanks to these tiny black holes, right?
It's a lot to wrap your head around, that's for sure. But that's what makes this research so fascinating. It brings together some of the biggest mysteries in physics.
It's like all the pieces of the puzzle are starting to, I don't know.
Click into place, yeah. And it all comes down to that memory burden idea. If that's right, then black holes, they don't just fade away neatly, they hit a cosmic speed bump as they shrink down.
Instead of vanishing, they become dark matter and send out those gravitational wave signals.
Exactly. And it gets even weirder because if this memory burden is real, it changes how we think about information in the universe too.
Because black holes, they're like the ultimate cosmic garbage disposals, right? Like what happens to everything they suck in?
And if they're not evaporating completely, all that information, it has to go somewhere, right? It has to be preserved somehow, which means we got to rethink what we know about quantum gravity, the theory that tries to bring together quantum mechanics and general relativity. And that's why detecting these high-frequency gravitational waves would be huge. We're not just talking about proving these mini black holes exist, we're talking about a whole new way to study physics at the Planck scale.
The place where gravity and quantum mechanics collide.
Exactly. It'd be revolutionary.
It's mind-blowing, honestly. This paper has really made me question everything I thought I knew, not just about black holes, but about the universe itself.
That's the beauty of science. Always challenging what we think we know, always opening up new doors. This paper, as wild as it is, it's just the beginning. Who knows what we'll discover next?